Okay, so I haven't done one of these videos for quite some time, and this particular video is going to be called Irrational Pi. And the reason why is, well, basically we're just going to show that pi is an irrational number. We're going to try and do that in quite a nice way. And I actually had a little video on it here, and I've copied this piece of code out on the side. So I've got that code copied, and what I'm going to do is attempt to replicate it. So I'm going to open up a Visual Studio Code, and I'm going to make a new file in here. So let's just do a new file, and I'm going to call it irrational pi.py for a Python for an actual Python file. And I will zoom in as well a few times. I'll get rid of the sidebar because we don't need it at this point, and I might even minimize this down here. So now that's nice for viewing. And basically I'm going to sort of like go through this code, but the important part is that I noticed that there was only a numpy and a matplotlib in there. And what it's actually going to do, the matplotlib, is going to draw a spiral going around. So we're going to attempt to do this. I'm using Python version 3.12. You can see my version down here, which is 3.12. So import numpy is the first thing that we're going to do, and we always import that with the alias np, and then import matplotlib .pyplot as plt. So pretty standard imports. And then we're going to create an array of theta values. So this is our little side comment here: create an array of theta values, and it's going to be done in degrees. Okay, and so theta underscore degrees is equal to np. So we're going to use the numpy module here, and we're going to do line space. And again, we'll see it again when I open up the brackets there, but return an evenly spaced number over a specified interval, and our interval is going to be from 0 and then to 113 times by 360. Now, oops, I put a plus there, times 360. So that's our interval. So we've got our start and our stop, and then our actual gap, which will be supports index, or make 10,000 of these. 10, 1, 2, 3. And sometimes we like to use an underscore in Python just so it's a little bit clear as to what we're doing. Now, why this was 113, not 133? Why 113? I'm not exactly 100% sure on that, but I'm going to go along with the actual code of it. But presumably it gets you round the actual, it needs to do that many rotations, and there's probably a good reason for that. So we'll look at that maybe later. The next thing we need to do is convert degrees to radians. Now, one thing that wasn't in the actual script that was written, so I'm writing this down as a script, is that normally, and I might actually do this, so I'll be doing mine slightly different, which is a template basically. So I've got a main template here. We like to have a main template, so you've got an if name equals main guard and run everything in our main module. So this is a main entry point of the code, and our imports will go there. So let's actually do that. So we'll move our imports down here. So that's our imports now, and the imports can go at the top. I should just move that little comment all the way to the top, so I just realized. And we will start to put all of this in our main function. But actually what we'll do is our main function, and it's all like be the main entry point of the code, X that, and we'll put that up here. So now we've got like a nice clean way. So when we come in, we run our main bit of the code, and all of this will go into another function. So we'll define a function, and we can now give our like worker function, we'll call it like our irrational, we'll call it irrational pi. So it's our irrational pi function will be here, and then we can put all of our code in there. So what I'm going to do is get rid of the return for now and hit tab. So now everything's going to go into our irrational pi function, and then the first thing that we're actually going to do is call, if I spell that right, irrational pi. The first thing now that we can do is call our function, so irrational pi. There we go. We've got a nice little entry point for our code, and then we call our block of code. So we can use this, and this is much more Pythonic, should we say. You can do scripting and write it as a script, and it's perfectly fine. But if you wanted to use it somewhere else, then it'd be much better to have it in the functional format. So, okay, so let's just do our radians then. So theta in underscore radians is going to be, let's have a look, np dot degrees. There's a degrees to rad over here. And if we see here that it says degrees to rad converts angles from degrees to radians, which is exactly what we like. X is array-like and so forth, so fine. It's going to take in our array, but we already know that we're getting an array here because this is an array. It's an ND. We can see over here it's an ND array. So perfect. That's just what we want. Theta degrees is going to feed in. So we're now converting all our degrees to radians. The next bit is we are going to separate the real and imaginary parts of Z. So we're going to be we're working in the complex plane, and I'm going to introduce some new language in here, but separate the real and imaginary parts of Z. And if we recall that Z basically is a complex number and it's made up of a real part, like a real part there, and then plus an imaginary, what's called an imaginary part, which is the square root of -1. Now I'm not going to call it imaginary because it's just basically an orthogonal number. So I'm going to call it the orthogonal part, and that's because if I was to draw, and I think I can draw in this over here, so if I was to draw, let me just get my drawing. That's we could imagine this as an axis, and there we go. I haven't drawn it very well. It's the most wiggly axis ever, but basically we've got an x component over here and a y component over here, and we say that x and y, they're orthogonal to each other. They're perpendicular. So things across this axis have no bearing on things on the vertical axis. Now, if I hit a double undo, right, triple undo, you know, this is our real number line here, the real number line, and these are all numbers that are multiples of the square root of -1. So this is over here the square root of -1. Now we can call them imaginary numbers and as in they don't exist, but the reality is that they do exist. They're just multiples of the square root of -1. So I'm going to give it a new name now. You've heard it here first. This is orthogonal numbers, right? They're not imaginary numbers anymore. There we go, orthogonal. However you spell it, orthogonal numbers. So they're just perpendicular and they're just multiples of the square root of -1. And it's as simple as that. So let's not complicate matters. So we're going to separate our real and orthogonal parts. Now the way that we do this is x equals numpy.real to get the real components, and there it returns the real part of a complex argument. The complex numbers are no longer complex. That's why, you know, I guess I'm averse to saying that they're complex. Also, one piece that I need to do before this, actually, before we separate the real and orthogonal parts, is we've actually got to calculate our Z number. So let's just do that. So calculate Z theta using the formula 1j. 1j is an imaginary, and is where 1j is the square root of -1, because that's actually what it is. I'm going to be averse to calling it imaginary. So we just set our z value and we say that it's numpy dot e np to the power of, so we want theta radians, and then times 1j, just like that, plus, so it's over here, if I can hover over it, there we go, let's just hover over that. This particular function calculates the exponent of all elements in the input array, so we are calculating the exponent e to the theta radians times by j, that's what it is, and then plus np dot exp to the np dot pi times by theta radians times 1j, again just like that. So now we've calculated or produced our z number, and we can say now that x is the real part of it, and we can say that y is the imaginary part, so np dot imaginary part, which we are calling the orthogonal parts, but we'll say Python uses old language now. So this is our orthogonal number. It's a number that effectively, if we had our, it's the number, there we go, that is x, and over there is y. Okay, we could call it imaginary, we can call it orthogonal too. So next part that we need to do is create a plot with specific settings, and we can do plot.figure, create a new figure, or activate an existing figure is what we're going to do. And we're going to set the figure size, so fig size, and we will make that a 10 by 10. There we go. So we are set a square of 10 by 10. That might be relatively obvious, but anyway, we've got it. And then plot, plt.plot. And then we're going to plot out our x component and our y component, and we'll have a color. Color equals and then white, just for a nice clean setting, and a line width equal to 0.5 there. I won't put a little comment on that because there's no need. And then plot.gca to get the current axis, and dot set underscore, if you can find it, set face color, there we go, set face color to black, so just some nice settings. So this sets the background to black. Which will contrast nicely with the white. And then plot.g, get the current axis again, get GCA, and then dot set underscore aspect to equal that will make an equal aspect ratio. We can play around with all of these different numbers. We're going to turn off the grid lines next, so plot dot grid, and turning off the grid lines will be a false. We turn that to a false, and plot dot x limit. We're going to set our x-axis limits to -2.5. These are just settings that are actually given, and 2.5, but we can adjust them. And we can also do, well, we'll copy that down, tab, paste that, because we can just do this for the y limit, just like that. So now we've got our x and y axis limits. And finally, we just got a plot dot show to show our actual chart. And that's pretty much it. So we can run our code. We're going to run from the main.py. It's going to call irrational.py, and it's going to go through everything. If everything's written out, we will be able to see what comes about from this. So let's just run our little piece of code and see what actually happens. We are launching, I believe, in launch mode somewhere. It's already completed it, and there we go. I wonder if I could actually slow that down or do an animation of it. But what we have here, or the whole point of this, is that if pi was rational, then these loops would just, so it's made up of thousands and thousands of loops. These loops would form a pattern, as it was, and they would like go over each other at a certain point in time. But with what we've got, that doesn't actually happen. They never go over each other. Now I just wonder if I can just change this number, so like 200, and just run this piece of code again, as in 113 wasn't special. Let's just run that, and again, there we go, get another version of the pattern. So we're going to get a few of these, and because it's called now in a function, I presume I could run a rational function a few times, which might be a nice thing to do. I wonder if I could open up multiple figures by doing that, but something like, we'll call this loops over here, which we'll say should be an integer, and here we'll pass in loops just like that, and we'll give it a default value of, say, 100, but yeah, and this is function to plot pi spiral, and then we can call that there. So if we call it without anything, it will do 100 loops, so we'll get the 100 loops just running like this. And that looks like that. So notice that each one of these patterns is like slightly different. And then we could do, and I could put this into a for loop, but let's just call our irrational pi again, and this time instead of having 100, maybe we'll put in just 10 loops. Let's just see what happens there. So the first thing we're going to get is our 100 version, and when we close it, it'll probably run the second one, which it does, and there we go, we get our 10 loops. And I think this one highlights it a little bit better, but we can see the gaps now between these two spirals. I wonder if I can actually zoom in. Can zoom in. There we go. If we sort of like zoom in, we can see that they just don't go over each other. So they just sort of like spiral around. You'll never get two lines that are on top of each other. So what I'm saying here is that pretty much that this line here, the red line, if I can trace it nicely, which I haven't, and the blue line, they just never go on top of each other. They're always slightly out, and that's because of the irrationality of pi. So I will actually close that, and we can maybe do a few of those, or maybe we could save the actual JPEGs down to have multitudes of them. But maybe we can do like a 1, a 10, or 100 is a default there. 100 and say 1,000, like that. and I wonder if we could even put in a 10,000. So paste that in, 10 underscore 123. See what happens. We're going to get 5 of these now that pop up sequentially one by one. I'm wondering if the last one's going to take forever to produce itself, because now we're going to have our array is going to be 10,000 times by 360. So if I pull out my trusty calculator and do 10,000 over here times by 360, we're going to get an array that is 3.6 million lines, 3.6 million values long. So that's not necessarily a problem generating the actual array in using numpy, but the part that it will actually be problematic maybe is actually plotting it onto our matplotlib. So let's just have a run of it anyway and see what actually happens in terms of performance. And we could do better than this. We could put a wrapper function around our irrational pi or a counter on it. So this is our first one that's just got one loop. That's what that looks like. And then it runs our second one, which is 10 that we've seen before. And then we run our third, which is 100 that we see. And then we go to, there we go. That is 1000, and look now how it looks white, but we do see these little speckles, these little tiny black freckles where it isn't like that. And then finally we've got 10,000 like that. So, and it produces another pattern. We're going to get a whole variant of these patterns. I doubt whether any of them are going to be the same, so nearly like snowflakes in a way. And that's the end. Our code has run, so that was actually relatively quick. Now we could modify and improve this. I'm going to leave that for people to put in the comments. If you want to put your comments in, that will be extremely useful. And if you found this video nice, put a thumbs up button, a like button, the favorite button, and recommend it, share it with friends. And that's basically it. So the irrationalness of pi in Python. Thanks for watching.